Go. Okay, welcome to chemistry with Dr. Stone here today. We're going to be learning about some periodic table trends, the four major ones we know you've all learned about. So the first one is atomic size. Now atomic size is, as you may have guessed, is the size of the atom itself. Now atomic size decreases across a period and increases down a group. It's labeled by this diagram, as you can see. It gets bigger as you go down this way, with fluorine being the smallest and francium being the biggest. Now there is a slight exception to this rule, that the transition metals, which are located in the D block right here, obviously this is not drawn to scale, but the transition metals are actually all very similarly sized. Not perfectly the same, but all relatively similar. So keep that in mind, especially on tests. That's a common test question. So the next one is electron affinity. Now electron affinity is actually the opposite of atomic size. It goes up this way. But what electron affinity is, it is the amount of energy released when an atom gains an electron. Okay, it decreases down a group and increases across a period, which, like I said before, is the opposite of atomic size. You always keep that in mind. And there's two major exceptions with electron affinity, is the filled S subshell and the half-filled P subshell. So the filled S subshell, which is right here, so you can have 3s2, gives extra stability for the element itself. And then the half-filled P right here. Now, an example of this would be phosphorus. I use the noble gas configuration of neon to get there faster. So 3s2 and 3p3, you see that the configuration is actually half done. Now remember that you have to keep the spins. You cannot have a double up spin within the same one. That's a whole different lesson, but you're Dr. Stone, you're gonna learn some extra stuff. So 3p3 which actually gives it extra stability, having a half filled. Now, next is electronegativity, which is how strongly an atom in a compound attracts electrons. Another note to make about this, also electronegativity goes in the same way that electron affinity does. And noble gases over here, so stuff like xenon and radon, do not have electronegativity values because they have a full octet filled, which means they're completely stable. Now they're not completely stable because they can still bind with other atoms. Xenon famously binds with fluorine to make a octahedral pattern, but they are so electronegative that they don't want electrons, so they're not going to attract them at all, which means that they have zero electronegativity value. Now electronegativity is very, very important for things like hydrogen bonding, because you need to know the three most electronegative elements. Fluorine is number 1, oxygen is number 2, and nitrogen is number 3. When these three elements bind with a hydrogen, they create hydrogen bonding intermolecular forces that are also known as van der Waals forces. These are the strongest of the van der Waals forces, especially if it's with fluorine. And fluorine will pretty much strip hydrogen of its electron and expose helium's positive proton, because helium only has one electron. Okay, and then it's also very important for making Lewis structures, because Lewis structures, you put the least electronegative element in the center. Now I actually have an example of this down here, but you can see that oxygen is the second most electronegative, but it's in the center. And you may ask why? Well, that's because it's bonding with fluorine. Fluorine's number 1. Fluorine will never go in the center. And oxygen, as you can see here, only goes in the center when it's with fluorine. Also with the chemical equation OF2. Now, ionization energy is the last one, is the energy required to remove an electron from an atom. This one also, just like electron affinity, has the filled S and the half-filled P shell exceptions. Atoms like fluorine have a higher ionization energy because they're only 1 away from a filled octet of 8. Just the 7s valence electrons are called halogens. They are 1 electron away from the noble gases, which is what your goal is to become. While sodium is lower because it's only 1 away from becoming like neon. So if you go here, and it can go back to neon. Like I said before, ionization energy also has those exceptions. Now, something to realize about this is that 3 of the 4 periodic table trends all go in the same direction. Atomic size is actually the outlier going from fluorine to francium, while electron affinity, electronegativity, and ionization energy go from francium to fluorine. That's just something to keep in mind, also something to help you remember. Well, this has been Dr. Stone with periodic table trends. Thank you for watching.